Hello again. This is Math 2-115 coming to you from the College DuPage, and this is the conclusion of the lecture entitled Algorithms. As always, please be an active learner as you watch this video. Last time we talked about the bubble sort and insertion sorts, and we made reference to a new higher powered sort called the gapped insertion sort or the library sort. And so here we talk just a little bit about it as a preview of coming attractions. So suppose a librarian were to store his books alphabetically on a long shelf, starting with A's at one end and culminating all along the way with no spaces between the books until he comes to the end of the Z's. Now, if the librarian acquired a new book that belonged in the B section, once he finds the correct spot in the B section, he would have to move every book over from the middle of the B's all the way down to the Z's in order to make room for the new book. Now, this is an insertion sort. However, if he were to, in the beginning, leave a space after every letter, as long as there was still space after B, he would only have to move a few books to make room for the new one. And this is the basic principle of the library sort. Now, one of the things we're going to be concerned about as we study algorithms are the class of algorithms, and this is a sorting algorithm. We are going to be concerned about what data structure to use. This ends up being an array, a computer array. We're going to be concerned about how does this perform in a couple of dimensions. What's the worst case? Here we're going to see that this is what we will soon call big O of n squared. What's the best case? This is big O of n times log n. What is the average performance? This is also big O in log n. And what is the worst case in terms of space complexity or memory? And this is big O of n. More later on these things soon. Greedy algorithms. Many algorithms we will study in this book are designed to solve optimization problems. The goal of such problems is to find a solution to the given problem that either minimizes or maximizes the value of some parameter. Optimization problems studied later in this text will include finding a route between two cities with smallest total mileage, determining a way to encode a message using the fewest bits possible, and finding a set of links between network nodes using the least amount of, in this case, fiber. Surprising, one of the simplest approaches often leads to a solution, at least a feasible solution, of an optimization problem. And sometimes being greedy is good. Not always, but sometimes. So this approach, which is called the greedy approach, selects the best choice at each step instead of considering all possibilities that might lead to an optimal solution. And these are called greedy algorithms. And once we know that a greedy algorithm finds a feasible solution, we still need to determine if it is the optimal solution. And we call the algorithm greedy whether or not it finds an optimal solution. So to do this, we either prove that the solution is optimal or show there's a counterexample where it doesn't yield an optimal solution. To make these more concrete, let's consider a specific example and consider an algorithm that makes change using coins. So consider the problem of making n-cents change, and we're using quarters, dimes, nickels, and pennies, and using the least total amount of coins. Now we can devise a greedy algorithm for making change for n-cents by making a locally optimal solution at each step. That is, at each step we choose the coin of the largest denomination possible to add to the pile of change without exceeding the amount we're making change for in cents. For example, if we wanted to make change for 67 cents, we start selecting quarters, and so we select a quarter that leaves 42 cents. And then we select a second quarter, which means we have 17 cents to go, followed by a dime, leaving 7 cents, followed by a nickel, leaving 2 cents, followed by a penny, and then followed by another penny. That would be the greedy algorithm. So this is the way we would do the greedy algorithm using any denomination of coins. And notice here, we're doing this in very general terms. So the procedure is, and this is a change-making algorithm, so we change C1, C2, all the way to CR. These are the values of the denominations of the coins. So you see we're letting that be general. So we're saying what coins are we allowing. And we are insisting that this is sorted, so C1 is bigger than C2 all the way down to CR. So those are the value of the coins. So then what we do is we do a do loop, and so we go from I equal 1 to R, and we have a count of the coins of each denomination. We start at 0, but as long as we have value left, what we can do is we can add another value of that coin, and then we just keep doing that, and then we go to the next coin, and this is n minus c sub I, where that is the number, where that is the value of the coin, and we go iterate there. And so we continue, and d sub I is the number of coins of each denomination c sub I that are in our change, for I equaling 1 to all the way to R. Now, that's the greedy algorithm, and in particular, when 4 denominations are quarters, dimes, and nickels, and so on and so forth, C1 would be 25. Then we go to dimes, nickels, and pennies. In this case, we will show that this does lead to an optimal solution. But before we prove this, we're going to show that there are sets of coins for which the greedy algorithm does not necessarily produce change using the fewest coins possible. For example, if we only have quarters, dimes, and pennies, and no nickels, the greedy algorithm that would make change for 30 cents would use 6 coins, a quarter and 5 pennies. But we could have used 3 coins, namely 3 dimes. So you see, instead of using 6, we could have used 3. So it does depend on what kind of coins you have to make change. Now this is called a lemma, and this is a result that we're going to use to prove the bigger theorem. So let's follow along with the proof of this. So if n is a positive integer, then n cents in change using quarters, dimes, nickels, and pennies, using the fewest coins possible, has at most 2 dimes, at most 1 nickel, and at most 4 pennies, and cannot have 2 dimes and a nickel. And moreover, the amount of change in dimes, nickels, and pennies cannot exceed 24 cents. Okay, we're going to use a proof by contradiction. So we will show that if we had more than the specified number of coins of each type, we could replace them using fewer coins that have the same value. So note that if we had 3 dimes, we could replace them, instead of with 3 coins, with a quarter and a nickel. If we had 2 nickels, we could replace them with a dime. And if we had 5 pennies, we could replace them with a nickel. And if we had 2 dimes and a nickel, we could replace them with a quarter. Because we can have at most 2 dimes and 1 nickel and 4 pennies, we cannot have 2 dimes and a nickel. It follows that 24 cents is the most money we can have in dimes, nickels, and pennies when making change using the fewest number of coins. So we have proven this lemma. You want to spend some time thinking through this proof and making it your own proof. So here's the theorem. We're going to prove that that greedy algorithm does produce change using the fewest coins possible. Again, we're going to use a proof by contradiction. So suppose there was a positive number n such that there's a way to make change for n cents using quarters, dimes, nickels, and pennies that uses fewer coins than the greedy algorithm finds. Well, first we're going to note that q prime, the number of quarters used by the greedy algorithm, must be the same as q, the number of quarters used by the greedy algorithm. So we're showing that the quarters must match. To show this, first note that the greedy algorithm uses the most quarters possible, so q prime is less than or equal to q. However, it is also the case that q prime cannot be less than q, for if it were, we would need to make up 25 cents from dimes, nickels, and pennies, and our lemma that we just proved says you can't do that, and so that's impossible. So you see, we know then that q prime is equal to q. And because there must be the same number of quarters in the 2 ways to make change, the value of the dimes, nickels, and pennies in those 2 ways must also be the same, because, and these coins are worth no more than 24 cents. So there must be the same number of dimes because the greedy algorithm uses the most dimes, and by lemma 1, when change is made using the fewest coins possible, at most 1 nickel and at most 4 pennies can be used. And so that the most dimes possible are also used in the optimal way to make change. Similarly, we can conclude the same number of nickels and finally the same number of pennies. Again, go through this and make it your own. A greedy algorithm makes the best choice at each step according to the specified criterion. The next example shows that it can be difficult, however, to determine which of the many possible criteria to choose. Okay, so suppose we have a group of proposed talks with preset start and end times. Devise a greedy algorithm to schedule as many of these talks as possible in a lecture hall, under the assumption that once a talk starts, it continues until the end. No two talks can proceed simultaneously at the same time, and a talk can begin at the same time that another one ends. Assume that talk J begins at time Sj, that is the starting time, and ends at time Ej, where E stands for end. So here is our solution then. To use a greedy algorithm to schedule the most talks, that means we're saying that is the most talks is what we're trying to optimize. We need to decide how to choose which talk to add at each steps. There are many criteria we could use to choose the talk that will happen that do not overlap with ones already selected. And we could, so for example, we could add talks in order of the earliest start time. We could add the talks in order of the shortest time of duration. We could add talks in order of the earliest finish times, or we could use some other criteria. Now, let's consider possible criteria. Suppose we add the talk that starts earliest among the talks compatible with those already selected. We can construct a counterexample to see that that does not always produce an optimal schedule. For instance, suppose we have 3 talks. Talk 1 starts at 8 a.m. and ends at noon. Talk 2 starts at 9 a.m. and ends at 10. Talk 3 starts at 11 and ends at 12. If we first select talk 1 that starts earliest, but once we've selected talk 1, we can't take either talk 2 or 3 because they both overlap. Hence, this greedy algorithm selects only one talk. That's not optimal because otherwise, if we did it differently, we could do both talk 2 and talk 3, which do not overlap. Now, suppose we add the talk that is shortest among the talks that do not overlap. Again, we can find a counterexample to show that this does not always produce an optimal schedule. So suppose that we have 3 talks. Talk 1 starts at 8 a.m. and ends at 9:15. Talk 2 starts at 9 a.m. and ends at 10 a.m. and talk 3 starts at 9:45 and ends at 11 a.m. We can select talk 2 because it's shortest, requiring 1 hour. But once we select talk 2, we cannot select either talk 1 or talk 3 because neither is compatible with talk 2. Hence, this greedy algorithm selects only one talk. However, it is possible to select 2 talks, talk 1 and talk 3, which are compatible. So you see, we've got counterexamples to those. So we've decided that that can't be the criteria that we use. However, it can be shown if we schedule the most talks possible if, at each step, we select the talk with the earliest ending time among the talks that are compatible with those already selected. And we're going to prove this in a bit using mathematical induction. And the first step we will do is to sort the talks according to increasing finish time. And so E1 is less than or equal to E2 and so on and so forth. We sorted them that way. And then the greedy algorithm is this one using that. Again, we haven't proved this yet, but here's the algorithm. So given the schedule, these are the starting times and these are the ending times. And we've sorted these because these are the earliest ending times. We sorted the talks by finish time and reorder them or renumber them if possible, so this is true. And then we start with the schedule being the null set. But then we go through and we start scheduling. So if talk J is compatible with the previously scheduled talk, then we add it to there and we start with J equal 1 to N with this ordering. And then we go to the next one and so on and so forth. Some of them we can't add, but others we can. And at the end, when we've gone through all the talks, when we've gone through J equal 1 to N, we return the set of scheduled talks. I will ask you to implement this algorithm, so make sure that you understand it. But now we're going to prove that the algorithm that we talked about was best. So what we're going to do is we're going to use induction to prove this. And often we will use induction to prove that algorithms are optimal. So this is a very important example. Okay. Now recall that the algorithm that we're using for scheduling talks is the one where we schedule this by earliest finishing time. So the input to this algorithm is a group of M proposed talks with presets starting and ending times. And the goal is to schedule as many of these lectures as possible in the main lecture hall so no two talks overlap. Suppose talk T sub j begins at S sub j and ends at EJ. And no two lectures can proceed in the main lecture hall at the same time, but a lecture in this hall can begin at the same time another one ends. So without loss of generality, we have sorted them in order of non-decreasing ending time. So the greeting algorithm proceeds by selecting each talk a stage with the earliest ending time among those talks that begin no sooner than when the last talk scheduled in the lecture hall is end. Note that a talk with the earliest end time is always selected first by the algorithm. We will show that this is optimal in the sense that it always schedules the most talks possible in the main lecture hall. And to prove the optimality of this, we're going to use mathematical induction on the variable n, the number of talks scheduled by the algorithm. So we let our statement be P of n is the proposition that if the greedy algorithm is used to schedule the talks, it is not possible to schedule more than n talks in this hall. Okay, so here's our basis step. So suppose that the greedy algorithm managed to schedule just one talk, T sub 1 in the main lecture hall. That means that no other talk can start after E1, and so otherwise the first such talk we would go through the talks in order of non-decreasing time. Hence, at time E1, each of the remaining talks needs to use the main hall because they all start before E1 and end after E1. It follows that no talks can be scheduled because both need to use the main lecture hall at time E1. This shows that P1 is true and completes the basis step. If you have one, if you're just scheduling one talk, you certainly can do this, and so that's what you're really doing here. Now, the inductive hypothesis says that pk is true. That says when k is an arbitrary positive integer, the greedy algorithm always schedules the most possible talks when it's scheduled to k talks, where k is every positive integer given any set of talks no matter how many. And we have to show that pk plus 1 follows from the assumption that pk is true. That is, we must show that under the assumption of pk, the greeting algorithm always schedules the most possible talks when it selects k plus 1 talks. Now suppose that it has scheduled k plus 1 talks. Our first step in completing the induction step is to show that there is a schedule including the most talks possible that contains talk t1, a talk with the earliest scheduled end time. It is easy to see because a schedule that begins with the talk T I in the list, where I is greater than 1, can be changed with the talk T1 to replace TI. To see this, note that because E1 is less than EI, all talks that were scheduled to follow talk TI can still be scheduled. Again, think through this, make this your own. Once we included talk T1, scheduling talks so that as many possible are scheduled is reduced to scheduling as many talks that began at or after time E1. So if we have scheduled as many tasks as possible, the schedule of talks other than talk T1 is an optimal schedule of the original talks that begin once T1 is ended. But the greedy algorithm schedules k talks when it creates a schedule, so we can apply the inductive hypothesis to assume, or not assume, but to realize that it has scheduled the most possible talks. It follows that the greedy algorithm has scheduled the most possible talks, k plus 1, when it produces a schedule with k plus 1 talks, and so pk plus 1 is true. That concludes the inductive step. So by the math induction, we know that P of n is true for every positive integer n. This completes the proof of optimality. We're now going to discuss the halting problem. And this is one of the most famous theorems in computer science. We will show that there is a problem that cannot be solved using any procedure. This is called the halting problem. And it asks this question: whether there's a procedure that takes as an input a computer program, and you cannot determine whether the program will eventually stop when run with this input. And this is convenient to have this procedure if it did, because then we could test a program and see if it ends up being in an infinite loop or not when writing and debugging programs. However, this was proven by the great mathematician Alan Turing that no such procedure exists. Before we present a proof that this is unsolvable, we first note that we cannot simply run a program and observe what it does to determine if it terminates when the run is given with given input, because if it halts, we have our answer for that one. But if it is still running, after any finite time has elapsed, we don't know if it would halt or if it would be an infinite loop. So you see, you can't design a program that will stop only after more than 1 billion years has elapsed. So Turing's proof is that this is unsolvable. It's a proof by contradiction, and we do have to use the concept of a Turing machine. So we're going to discuss this before the proof. And so we're going to talk about a Turing machine. Here's some biographical things. He's a very interesting fellow. I'm skipping that in the interest of time, but there was a movie that's reviewed shortly down here. It was called the Imitation Game, that is about one of Turing's greatest triumphs, cracking the code during World War II. Okay, but Turing's machine basically is infinite because you have an infinite tape, and the machine goes infinite in both directions, and it basically gets away from the problem of having only finite memory. And so any computer that we have is a Turing machine, but there are Turing machines that aren't any computer. So Turing machines are much more powerful than real computers, which have finite memory capabilities. So here's the proof. Assume that there is a solution. Again, this is by contradiction to the halting problem. And that is a procedure that is called H for halting. And there's the program, and there's the input to the program. So it's program and an input. Now this takes two inputs, one a program and the other I. But what we're going to do is, since the program itself is a bit stream, we're going to say, let's consider P as the program, but also the input. So we're going to be talking about HPP. So to show that no procedure H exists that solves the halting problem, we take a simple procedure which is called KP, which works as follows. And it makes use of the output HPP. If the output of HPP is that it loops forever, because we say that we do have a halting problem solution, that means that P loops forever, given a copy itself as input. But that means that KP halts. And if the output HPP is halt, that means it really does end. That means that P halts when given a copy of itself as input, so that means KP loops forever. That is, KP does the opposite of what HPP does. Now suppose we provide K as input to K. So we're going to say what happens when we have K of K. And we're going to summarize that on the following chart. So the input is P as a program and P as input. Okay, and so this is going to be, and we're doing this in the program KP. Well, we have this, so the output when P is the program and P is input is HPP, but this goes into K of P. But if HPP halts, then this says it loops forever. If this says it loops forever, then KP says halt. So by definition of K, we see that K of K either loops forever or halts in violation of what H tells us. In both cases, we have a contradiction. Thus, H cannot always give the correct answers. Consequently, there is no procedure that solves the halting problem. Here's an LSA for you guys to do. I'll assign a number to this soon and post it. Okay, so there are three things to do. Show that if there were a coin worth 12 cents, the greedy algorithm would not always produce change with the fewest coins. Use the algorithm for talk scheduling, that was the algorithm 7, to schedule the largest number of talks if this is the talks that we have to do. So you're implementing the algorithm. And the last problem is show that a greedy algorithm that schedules talks in a lecture hall, as described in the example, by selecting at each step the talk that overlaps the fewest other talks, does not always produce an optimal schedule. That's going to be by counterexample. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.